right, my friends, part 2, this will be the shortest piece of this section. It's about what's called rectangle approximations. First, let's give you a general idea of what the different types of rectangle approximations for and what they are in general. So basically, here's the idea. Let's say you have the graph of a function. I'll do for any function, and let's say you are trying to figure out what's called the area of the bounded region on a given interval, and bounded between the x-axis and this given function. So if you look at the shape that I have here, so pretend that line right there is perfectly vertical. But anyway, if you look at the shape that I have here, it's not the kind of thing that we have a geometry formula for. It's out of the scope of what we learned in geometry. But the idea is that if we don't have a perfect geometry formula for it, then maybe we could use a very simple geometry formula. And what's the simplest one? I'm just going to go base times height for a rectangle. So the simplest geometry formula for area, I would say, is base times height. And we're going to use a certain number of rectangles to approximate, the area of a given region. So, and there are different types of ways to go about it. So let's say I'm going to use, so we have this interval from A to B, and you can separate your large interval into different sub-intervals, and typically the sub-intervals are equally sized. So let's say I decide to split, this into 3 sub-intervals. So from A to, whatever this is, and then this little sub-interval, and then this third one. So what we could do then is use different types of sums to approximate the area. So there is what's called a right sum. Now, a right sum would be where every time you're given a choice on like a subinterval, so let's say from A to whatever this number is here, you would always choose the x value that's on the right, plug that into the function, and that would become the height of your rectangle. So a right sum, if I was using a right sum and 3 subintervals here, then my first rectangle would look something like that. And then again, a right sum, if I have my choice of this x value and this one, I would plug in the one that's farther to the right and then plug it in to the function. And that would be the height of my second rectangle. And then again, if I'm using a right sum, then for this third subinterval, I would plug b in because that is the x value that's farthest on the right of this subinterval. And then that would become the height of my third rectangle. And the idea is that if I was to calculate the area of each of these rectangles and add those areas together, then I'd have maybe a decent approximation for the area of the yellow shaded region. And I think it actually would be pretty decent in this case. You've got this little extra part that wouldn't be considered in your calculations. Maybe it's kind of similar to this white part that that was kind of, so you've got, you've got an under approximation and then an over approximation, and maybe they kind of balance each other out. And then here you have an under approximation, and maybe it kind of balances out this over approximation. So, but anyway, the point is that that's what a right sum looks like. Now I'm going to go ahead and erase this kind of like extra piece off here. Maybe erase that little height part off. And now let's talk about what would a left sum look like. I'll use another color here, so maybe pink. So a left sum, same story, just this time it's the x value on the left every time. So left sum on the first subinterval, you would have plugged a in for the height of your rectangle. So this little piece right here, that would have been, you would have calculated that area when you're doing your rectangular approximation. From this number to this number, you'd pick the number on the left. And then from this number to B, you'd pick this first number because it would be the number on the left. Plug that into the function, and then, so what I have here in pink would be what a left Riemann sum approximation would look like for the area of the shaded region. So there are other sums which I'll mention as well. There's a midpoint sum, and my picture is getting super messy. I now realize as I'm in the middle of this that some of you guys are probably pretty annoyed with me right now as you're trying to take notes. Sorry for that. Anyway, so there's such thing as a midpoint sum, and we can talk about that in a little bit. There is an upper sum, and then there's a lower sum. And there are other types of sums. There's a trapezoidal sum and something like a parabolic sum and all sorts of crazy stuff. But I think if you have an idea as to what these are like, then we will have accomplished what we needed to accomplish today. All of these types of sums are using rectangles each time. And so if as you take notes, if you don't feel like you have to go back and re-scribble all over this picture every time, if you just have a picture of one of the sums, like let's say your picture looks like this, and then you could like draw an arrow and be like, this is what a left sum looks like. You could kind of release yourself from the misery of what I'm doing, erasing and then redrawing. Just a couple of comments though. I'll use orange for the next one. Let's say I'm doing, I'll go ahead and go in order, I guess. Let's say I'm doing a midpoint sum. Then if you have 3 subintervals, a midpoint sum, every time you would actually find the midpoint down here on the x-axis, so between A and whatever that is, you'd average those numbers, and then you would plug that number into the function rule. That would become your height, and then you'd use the normal width that you would have for any of the other rectangles. So again, on the second subinterval here, midpoint sum, find the middle down here on the x-axis, plug that in, that becomes the height of your second rectangle, and then again midpoint down here between this number and B, plugging that in. Oh wait, there's the function right there. It's getting so scribbly I don't even know where the function is anymore, so sorry about that. Anyway, so that's what a midpoint sum would be. An upper sum, I'm just going to mention these real quick. Upper sum, you would always pick the higher of the y values on any subinterval and use that. Upper sum is always an over approximation. And lower sum, you'd always use the lower of the 2 y values and use that. A lower sum is always an under approximation. So that's just kind of in general what these are. And now let's kind of get started on some examples where I have you practice doing some approximations. So example, I think this is a continuation from the last one, and this would be example 4. Yeah. Okay, example 4, let's have you, let's give you a picture here. So, let's just use a really simple function rule. Let's do f of x equals x squared. So, okay, so then, so I've got a bit of a warped scale here. Okay, so let's graph f of x equals x squared just on the interval from 1 to 2. So this is the graph of f of x equals x squared. And I'm going to shade the region bounded by f of x equaling x squared and the x-axis on the interval from 0 to 2. And I'll just shade it in. So this is the area, this is the region that we're going to approximate the area of. So as you can see, not the kind of thing that we would have a formula for from basic geometry. Most people wouldn't anyway. So the directions, for example, are going to be for you to use we'll practice using a right endpoint sum. This one. Because when it comes to doing this a lot, this is kind of the go-to. Use a right endpoint sum with n subintervals of equal width to estimate the area of the shaded region. Okay, so let's see, part A. So it says n subintervals of equal width. So for A, we'll have n be 2. We'll keep the number low because this can get really tedious really quick. Okay, so if n is 2, then remember that, so subintervals of equal width, so your entire interval is just from 0 to 2. So we'd be talking about going from 0 to 1, that's your first subinterval, and then from 1 to 2, that's your second subinterval. So looking at this, and then this also says that you want to use a right endpoint sum. So between 0 and 1, 1 is farther to the right, so you'd plug 1 into the function and then use that for the height of your first rectangle. On your second subinterval from 1 to 2, it's a right sum, so you're going to plug 2 into the function rule. That becomes the height of your second rectangle. And the width of the rectangle is always the full width of the subinterval. Okay. And I hope you can see here that this is a horrible approximation for the shaded region. There's a lot of extra stuff that we're going to have. So we're going to have a gross over approximation, but at least we're showing that we understand what's being asked here. So, so for n equals 2 here, we would say, please don't say that the area is exactly equal to. Please say approximately equal to. It really shows that you understand what's happening here. So the area would be approximately equal to, the first rectangle has a base of 1, and then its height would be just 1 squared, or 1. The second rectangle would have a base again of 1, and then the height would be 2 squared, or 4. So if we are using just 2 rectangles in this case and using a right endpoint sum like the directions said, we would say that the area is approximately, it looks like 5 square units. And so what might be good for your brain right now would be to maybe guess, guess what the real area is of this shaded region. And we'll see, and also think about how could we use a method a lot like this, but get more accuracy sooner, like reduce the error, essentially. So for part B, what if n, the number of subintervals, a lot of people would say, hey, if you want less error, you're going to need more rectangles if you're going to be married to this concept. And we are somewhat married to this concept for at least for a little while. Anyway, so let's say we go to 4. We increase the number of rectangles to 4. I'll use... let's do purple here. Purple's pretty. Okay, so if you're gonna do 4 subintervals, then that would be 4 rectangles. So each one would end up needing to be, so you've got 2 units, 4 rectangles, all evenly spaced, evenly wide at the bottom, or having the same width at the bottom. So each one would have a width of 1/2 this time. So I'm gonna erase this extra pink or extra orange off from the last part so I can show. Okay. So your first rectangle, it's a right sum, so you're gonna plug in 1/2. Second rectangle, again, right sum, so you're gonna plug in 1. Third rectangle, you would plug in 3/4. And then the fourth rectangle, you plug in 2. Like so. Okay. So if you're using 4 subintervals of equal width, still a right sum, then you would say that the area is approximately, so rectangle number 1, the base is 1/2, and then you could multiply it by the height, which would be 1/2 squared or 1/4. Now really quick, I'm going to do a little move that we'll use quite a bit later. Since all the bases are 1/2, you could factor kind of that base value out and then just have the sum of all the heights in here, because you'd end up with 1/2 times all the heights, which would give you all the areas. So I'm just factoring the common base value out. So 1/2 times 1/4 is the first rectangle. 1/2 times 1 for the second rectangle. 1/2 times, and you'd have to do 3/4 squared to get the height of this one. So that would be 9/16. And then 1/2 times 4 to get the last one. So if you simplify this, probably the easiest way would maybe be to like not worry with the 1/2 quite yet. 4 plus 1 is 5. 1/4 is the same as 4/16, so you could add it to the 9/16. So would that be 13/16? Would that be 13/16? I think so. So 5 and 13/16. And then you could just take half of each or something fun like that. Did I do that right? No, I have a mistake somewhere. Oh, it's right there. When you square, that should not say 3/4. There we go. That's what it is. What should that say? 3/2. There we go. And then when you square 3/2, you get 9/4. Oh, yay. Okay, some of you guys have been like itching, I'm sure, watching that. Okay, sorry. Okay, all right, let's try this again. 5, and then that would be our 10/4 or 2.5, so that'd be 7.5. There we go, there we go. Okay, so that'd be 3.5 plus 4, so 3 3/4. There we go. That's kind of a little more, that makes a little more sense. So if you use a right endpoint sum, the area would be approximately 3 3/4 units squared. There we go. Okay. All right, my friends. Let's just do one more just to make sure you'd be okay with maybe something like a midpoint sum or something like that. Let's see. Example. Let's see. Okay. Example 5, I guess. Find the area of, not find, I'm sorry. How about approximate? Wow. Sorry guys, my hand is not doing what I really want it to do right now. Let's try again. Okay. Approximate. Just gonna think really hard right now. Okay. Approximate the area of the shaded region from example 4. That way we don't have to draw so much. Using a midpoint sum and 2 subintervals. Of equal width. There we go. Okay, good time to pause the video and see how you would go about it. I'm just gonna go ahead and like kind of go back on top of this picture and use it again. Okay, so a midpoint sum using 2 subintervals of equal width. So your subintervals this time are going to be from 0 to 1, and then from 1 to 2, since they said 2 subintervals, from 0 to 1, the midpoint would be 1/2. So you would plug 1/2 into the function, and then that becomes the height. But the subinterval 0 to 1 is the full width. So that would be rectangle 1. And I hope it makes sense. Your number of subintervals will always equal your number of rectangles. And then your subinterval from 1 to 2, the midpoint would be 3/2. So you'd plug 3/2 in, and then your rectangle would use up, again, the full width of the subinterval, like so. Okay, so in that case, we would say the area is approximately, rectangle 1 would be just base times height. I hope it makes sense. The base is 1 both times, so I'm just going to show that I thought that through. And then I'd multiply that times the height on the first one, which would be 1/2 squared or 1/4. I'd multiply 1 by the height of the second rectangle, which would be 3/2 squared or 9/4. And so you'd end up with 10/4 or 5/2, which is 2.5. And so a midpoint sum, a lot of people don't like it because you have to think a little harder. But I hope you can see that even though we only had 2 rectangles, a midpoint sum typically has over and under approximations that sort of cancel each other out. I guess depending on what your graph looks like, but typically a midpoint sum, you get a lot more accuracy even though you're using fewer subintervals. So anyway, I'm just going to add a unit squared on here and call it a day. All right, at this point, you should feel pretty comfortable doing your part 2 homework problem set for section 11.5. It's really just this concept, and then in part 3, we'll take it a little farther. All right, my friends, I hope this helps. Take care, everybody.